We'll come to the topic, which is IRS training in multi-user scenario, right? As the other speakers spoke, that in multi-user scenario, it has not been studied much, right? So I'll also be concluding like the same when we have multiple users and we have multiple access like TDMA or FDMA, right? So then the things have not been studied enough. So let us start with the IRS, right? So already it is known that it's a array of passive elements, right? So they can be reconfigured so that we can get a better signal at the receiver, right? So it's a single user, and when we have multiple users, right? So then from the base station to the IRS, it would be a single channel, right? So the same channel, the signal goes there, right? The difference that will come, right? So that is from the IRS to user 1 and IRS to user 2, right? So how can we serve these two users or maybe more than that, right? So we need to set the phase shift matrix for each of these elements in such a way that we can maximize the received power at both the users, right? So the simplest scenario in this type of system can be through non-orthogonal multiple access. So where we can have a single signal actually, which is combination of the two signals through different power allocation coefficients, right? So when we use transmission in the non-orthogonal domain, right? So then the mixed signal, right, that may be we have represented as X, right? So that is transmitted from the base station and the two users, and which is near user and that is far user, right? They can be served. So the first scenario, right? So that was proposed was like this, in which the near user, which is direct link is available from base station to the user, while in the far user case, the direct link is blocked and it is served through the IRS, right? So in such a case, the problem is very simple. We need to define, we need to just find these phi's for only corresponding to the far user, right? So in that case, it is as simple as single user case for the IRS training, right? So here, when I mention IRS training, I mean to say that the deciding the phase shift matrix, right? So that is what, right? So in this case, right? So what we want is all the elements, right? So when link to both the users is blocked, right? So in that case, there are strategies like there can be element splitting, right? There can be two different IRS to serve two different users, right? So I'll explain different cases, but right now what we want, right? So what we want is we want to take full advantage of the IRS, and so that all the elements of the IRS should serve to both the users in an optimum way. And for that, right? So the limitation of an IRS element is that only single phase shift we can specify, right? We cannot say that, okay, for user 1 you have some phase shift phi1, and for user 2 you have phase shift phi2, and that too at the same time, right? That is not possible, right? So how do we design, right? So let us say we design that to maximize the sum received power, right? So sum received power is if we have received signal like this, right? So there are k number of IRS elements. We have cascaded channels and the phase shift of the kth element, right? So when we say normal transmission is there, we have the signal transmission, right? So it's like that, and the sum received power, that is the received power at user 1, received power at user 2, right? So here this H1 and H2, that is nothing but the cascaded channels, right? So cascaded channel. So we have considered this mixed product of those two channels as the H1 or H2, right? So now we have represented it in the vector form, right? So now we want to have single phase shift, right? So and that should maximize these received power, right? So when we were simulating this, right? So we had an observation that when we if we design the phase shift phi just looking at user 1, right? So in that case, it doesn't interfere user 2. And when we design looking at user 2, right? So then it doesn't interfere user 1, right? So that is mainly because there are when k is very large, right? So then if we take relay fading, right? So relay fading, either this link or this link. So either of this link is relay fading, then the sum of the signal, right? It comes out to be 0, right? So if we consider this user, we maximize the signal at this user, then for this user the sum comes out to be almost 0, right? So if not 0, almost 0, right? So that is what we thought that okay, let us do this sum received power and represent it in this fashion. So vector sum, right? So that is we use the vector sum identity, right? So vector sum identity we use, and this sum is less than this, so basically that is triangular identity. So then using this we maximize this. When we maximize this, we know that this phi, right? So it has to be proportional to the remaining quantity, right? So it is just the dot product of two vectors, right? So we can say that inner product of two vectors. In that case, that will be maximized. That will be maximum when the two vectors they are in the same direction, right? So that is how we got this phase shift, right? So this phase shift, this phase shift matrix, when we use this, right? So then we get the some received power, right? So that is maximum. But in fact, when we when we verify, right? So it is actually maximizing the power at both the users, right? So that is we have not proven, but we just got it through simulations. Okay, so we have three scenarios to compare with, and that summary is over here, right? So in the first scenario, we have a single IRS, right? So where we did any element splitting, right? So element splitting is half of the elements will serve user 1, half of the elements will serve user 2. Another scenario, we have two separate IRS with k by 2 elements each, right? So when you have k by 2 elements each, and each IRS is serving each user, while this one is the our scenario, right? So when we compare this performance, right? So it's a system throughput, right? So a system throughput or the equivalent performance we will get when we try for the sum rate, right? So we are getting the better performance in the proposed scenario, right? So the main reason is each element of IRS is contributing to the performance, right? So that is what is the observation, right? And scenario B, right? So it performs better than scenario A in throughput, right? So it is because of the IRS positions, right? So IRS positions we can put in favorable locations so that it gives a better performance at the user, right? So that is the non-orthogonal multiple access case, right? So that was the case. So this is just the outage probability performances for different number of IRS elements. Yeah, and then yes, so that was the non-orthogonal multiple access case, right? So what if we have an service to multiple users in orthogonal fashion, right? So then we have teams like time division multiple access, frequency division multiple access, and code division multiple access, right? So these are the basic multiple access techniques wherein we have even the latest techniques, right? So if we use OFDMA, right? So in that case, we need to train the IRS for every subcarrier, right? So that is already mentioned out by Professor Brijesh, and so in when we have frequency selective channel, basically the wideband channel, right? So in that case, what challenges would be there, right? So basically TDMA, right? So we have within one coherence time or within one frame, we have data of multiple users. When we have data of multiple users, different users will have different phase shift required, right? So basically, we need to change the reflection coefficient of different elements within a frame, right? So we have guard interval between two frames, but within the frame between two users data, we don't have guard interval. So whether do we have time required to shift the other thing, right? So that is frequency domain multiple access, right? So frequency domain multiple access, if we have, so different frequencies, right? So different frequencies, different users are served. So in that case, whether the phase, we don't have any issue in the magnitude spectrum, right? But we have phase spectrum, right? So phase spectrum will have different values, and whether the metamaterials, right, that are available till now, or the reconfigurability that we have achieved, right, whether that will allow to have that type of phase spectrum, right? So that is also an open question, right? So these are what the considerations that we can have in the multiple user scenarios when they are served through IRS in the orthogonal fashion, right? So non-orthogonal fashion, when multiple users are served through IRS, right? So there is not much of a challenge. We just have the signal power and some of the signal power, and then we optimize the phase shift matrix, right? So that can be optimized, right? But then the practical questions, right? So that comes when we have multiple users being served through single IRS and in the orthogonal fashion, right? So I think, yeah. Then for the CDMA case, right? So CDMA case, right? Maybe we can have some parallel training if we have different users which are assigned orthogonal pilots, right? So then maybe different users. Here we have shown that multiple elements, right? So they have the signature sequences which are orthogonal, which are, here I have not shown orthogonal, but if orthogonal is shown, then we can separate the signals, and we can do the training, right? So but then if we have training using CDMA approach, and if we serve, right? So then if we serve with either FDMA or TDMA, right? So then it would be a wideband training and narrowband serving, right? So how will the system behave, right? So that is again an open question. So yeah, so I think it comes to an end, right? Yeah, thank you.
Long live India and France friendship.